to my workshop. My name is Robert. This video is part 4 in the series on the Ainjest rapid threading attachment. In this video I'm going to demonstrate cutting some threads with it. Firstly, I'll grind up a carbide insert for use as a cutting tool. Then I'm going to cut 2 imperial and 2 metric threads to demonstrate it. Hope you enjoy it. Let's get on with it. So in order to try out threading at high speed, I think I'm going to need a carbide threading tool. Now, I don't normally use carbide threading tools and I'm not about to start buying lots of them. So what I've done is made up this is a homemade holder, and we have a DCGT insert on here. Now, if you were to look very carefully at the ends, you'd see that this one's completely and utterly ruined, so it's no great loss. So I'm just going to grind this away and form this into a 60-degree tool. Now, a DCGT or DCMT tool has 55 degrees on the point here, which is very, very close to the 60. It would actually be ideal for a Whitworth thread as it stands. But I can simply flatten off all of this positive relief here and then reshape the end to get this into a 60-degree point, so it will cut very nicely, much like a off-the-shelf one. The holder, which I'll take the screw out, try not to lose it. This holder, this is a homemade jobby. Now, this was relatively simple to make. Rather than just keep buying holders, all it required was a bit of scrap steel and a little bit of time to mill it. So if anybody's interested in the process I went through to make this, then let me know in the comments and I'll make a video on it. So this is the fixture I'm going to use to grind this tool up. I've got a resin bonded diamond wheel on here, which should give a reasonable finish on the carbide. First things first, we'll rotate it round this way. Rotate it to 90 degrees. You'll notice I've got some extraction at the back here ready to go. Grinding carbide's not particularly good for you, so you need to take care. This will go into my shop vac, which is full of a lot of oily chips, so that should catch all the dust very nicely. Apologies for the background noise, but we're in the middle of a heat wave here, and I've got all the windows in the roof open, and so you can hear all the noise from the surroundings. This is the result of the first grind. I'm going to repeat on the other end. So I've got multiple parts that I can chew my way through. Okay, now to grind the sides. We'll first set this angle to about 7 degrees. That's roughly what the angle on the side is there. And we'll rotate this top part round to an angle of 30 degrees. which is there. And that's all it takes to grind that side. So now we'll bring the tool away. So for the next side, rather than flipping the tool in the holder and rotating the holder around the other way, one way that I do it, in order to make sure that both sides are exactly equal angle, is to simply take the tool out, turn it upside down, and then we'll rotate the fixture to give the clearance on the other side. We can get this to focus. That's what we've achieved there. Just check that nothing's going to crash. And there we are. So let's see what we've got. That's at 60 degrees. We've got about 7 degrees on that side. And similar on this side. Final thing to do with these inserts that I've ground up is just break the end. So I've got a diamond stone here, and I'll just I don't know whether you can actually see that. But there's just a very slight radius on it as opposed to that one having a sharp point. So at last, I'm ready to demonstrate this Ainjest working. Let's go through each of the setup stages in turn. Firstly, our workpiece. We have a length turned down to 1/4 inch here. I'm going to put a 20 TPI thread on it. And we have a length here turned to 1/2 inch. I'm going to put a 13 TPI thread on this. So let's first set up the quick change gearbox. We want 20 TPI, so C3SY. C3SY. And now if we just revolve the chuck, you can see the lead screw is turning. The lead screw on this machine, if you put the selector in the position X for feed, the lead screw is disabled. I have my compound rest set at 29.5 degrees to the perpendicular to the axis of rotation. So that's on about 60.5 degrees on the scale here. I usually run it at in this configuration. I tend to feed with the compound rather than using everything on the cross slide. As with HSS tools, I find I break fewer tips while I'm cutting threads this way. And now we'll get the tool on centre height, so I tend to use a centre in the tailstock and bring that in close, don't actually touch it, and eyeball it from the side until it looks like it's exactly on the same level, something like that. So we'll install the tool in the correct position on the tool post, and to check it's lined up I use a parallel here, one side against the flat face of the chuck, the other one against the side of the tool holder. Now the tool holder has been milled so that the turning insert lies in a straight line along parallel to the side here, so that insert is now correctly positioned. And for these demonstrations of cutting an imperial thread, I'm not going to be using a threading dial, so I've removed it. So just to prove we do not need it. This is the tool bit I'll be using, and if we put something underneath it so you can see, there's a cutout on the left hand side. I've ground this extra material away on this insert to try and enable it to get closer into the shoulder, like that. About there, and that's about the point at which I want to stop threading. So having set up the tool roughly in the position where I want to stop the threading, I'm going to back it right out. Now what I'm going to do is to manually rotate the chuck by hand until I can engage the Ainjest. This takes quite some time because it's there. Right, we are now engaged. So if I bring this in closer, as I wind this round, you can see the tool has now moved slightly. Right, so let's leave it like that for the time being. Now you've actually got a better view of this than I have. This is pretty impossible to see, but I now have to go in, try and find out where we are under here. I'm pretty unsighted for this. I have to loosen off this bolt and then move this block, and I'll push it until, just easing it with my finger until the Ainjest releases. Should be about there. Suddenly got very tight. Push it right up there. And that's done up tight. So if we rotate the chuck by hand, that's just a shade too early. So now we know that this is in roughly the right position. I just want it back about 1/16 of an inch. Just tighten that up there. And then do that up really tight, because if that comes loose, there's going to be a large crash. So now all that's set up, That's well clear of everything. Let's move back. I'm going to turn on the lathe at about 300 RPM, 370. I'm going to engage the Ainjest and I'm going to let it trip out where it wants to trip out. So I'm going to wind this right in, and you can see that I've not quite got it right. So we'll repeat the process until we're just in just the right position. Okay, adjustment made. Let's check it out. At this point I'm just going to use the compound slide to advance it just to the position I want it to be. So that'll be good. Right, I'm going to feed in with the cross slide. An in feed of about 22 thousandths should be enough, and I'll check it with some thread wires. So let's start with 5 thou in feed, and off we go. Time to check this thread. I'm going to do this in a couple of ways. The first, I'm going to use some thread wires. Now, to get the target dimension, I've been to theoreticalmachinist.com, and there's a thread calculator for UNC threads there, and it tells me that for this 1/4 thread I'm looking for 0.2601 to 0.2564 over 29 thou wires. So here's our 29 thou wires. I'll drop that one in there, and just gently do that until that's just tight. Give that a lock, put your hand under, move that away, catch the wires, and the answer is 0.261, so I'm 1 thou over the biggest dimension. The second way I'm going to check this is with a thread micrometer. I realise not everybody's going to have this sort of thing. This was a cheap eBay score actually, so doesn't get used very often, but we shall give it a go and see if we get the right answer with it. And that's saying 0.218, which will be the pitch diameter. According to the calculator on Theoretical Machinist, this should be about 0.2164 maximum. So got another thou or two to come off. That thread should be good. Let's measure it in the two ways again. That's 0.2155 or something, which is just underneath the maximum. .2545, which means I've undershot by about a thou or so now. Just as a little confidence check, here's a 1/4-20 nut. There we are. It fits all right actually. Pretty typical of what you get on a normal bolt. So that's 20 TPI. Now I'm going to repeat the same process on here without the threading dial, and this time I'm going to do a 13 TPI thread. This is 1/2 inch, so this will be a 1/2 13 UNC thread. So I've just set up the stop for this shoulder here instead, and I've fine-tuned the position with the compound slide, which is at an angle, so it gives us some side-to-side adjustment. So we are now tripping out, hopefully just here. Let's just verify that. That should be good. Back to the threading chart, and for 13 TPI we are at C7TY. So C, just spindle in neutral and rotate things to make it easier to change. 7 T, and we're in Y already. As before, no threading dial. So these are my scruffy notes about what we're trying to hit. For a 1/2 13, we need an OD of 0.498 to 0.4877. The pitch is within this range, and we need some 45 thou wires, which are the closest to the ideal size, and our measurement should lie between these two figures here. So I'll measure it with wires again, and I'll try the thread mic because I have an 8 to 13 TPI thread mic as well. Let's wind the speed up to 800 RPM, clean off the tip of the tool, and do a couple of trial runs just to see everything works. The stopping position is clearly dependent upon the speed, which is something worth bearing in mind. So I've used the compound again to back it out. Let's touch off and try again. Well, there's the thread so far. It does look particularly horrible. The material is whatever scrap came out of my scrap bin, so I've no idea what it is or what its provenance is. So I might do a few spring cuts and a few gentle passes just to see if we can clean it up a little bit. And that says 460, so it's another 12 thou to come off. Let's see if the thread wires agree. And that says 527, or just under 527. So that says there's another 10 thou or so to come off as well. And that, ladies and gentlemen, is what happens if you actually try and manually release it because you don't trust it. Hey ho. Well, if it'll focus, the thread still looks disgusting. I think the tip of the tool has survived, which is good. Without cleaning up and without measuring, let's just try this. This is a 1/2 UNC nut off of my drawbar. seems to be alright, not too much play. Thread wouldn't win any prizes for quality, but that may be down to the material, maybe down to the insert, given that it's home ground, or maybe down to me. So time to get the threading dial assembled. As you can see, this linkage that I've made up here, this little bar here, allows this to swing around and accommodate different pinions on the back of the threading dial. Now, if we have a close look at the data plate here, I'm going to be cutting a 1mm pitch thread. So I will be using position A, which is here. I can engage the nut on one number only, and I need a 20 tooth pinion, and this is one of my homegrown 20 teeth pinions. So I'll take that off. Wiggle the pinion, push it in deeply, and then just back off a hair so that there's a little bit of backlash in the system. And that's ready to go. This time on the threading chart we're looking for 1mm, which we find up here, and we need to set this to AR3W. That's already on A. R. Make sure the spindle is free so everything can be engaged properly. Rotate this round to 3, and W. W gives you metric threads, Y gives you imperial threads, X gives you just feed only. So I've got a piece of steel in the lathe here that I've turned down to 10mm. On this section I've provided a run out groove for the threading tool to drop into at the end of the cut. I'll be using the Ainjest 1mm pitch thread, nothing much unusual you might think. Here's the difference. I'm going to be opening the half nuts and winding the carriage back with the carriage wheel. I'm then going to be re-engaging the half nut using the Ainjest and picking up the thread correctly every single time. Now, to make sure that I don't completely screw up the thread, because normally you can't re-engage the half nut on a metric thread on an imperial lathe. This is a 4 TPI lead screw. This is a 4 pitch gauge, and you can't really see that. It fits on there absolutely perfectly. Normally you can't disengage the half nut and re-engage it because everything gets out of sync. However, the main difference here is that on the back here there's a 20 tooth pinion, as it indicates here. So this is a 1/4 inch from one crest to the next. 20 teeth will require this to move a lead of 20 times 1/4 inch, which is 5 inches. 5 inches is equal to exactly 127mm, because the inch is based upon metric definitions now. So if I re-engage this after 5 inches of movement, if you like, on the lead screw, I'll be bang on the 1mm pitch still. So as long as you have an integral number of pitches of the thread you're trying to cut moved by the lead screw thread, you can re-engage the half nut. On here you can see there are a whole raft of other metric pitches that you can use this dial for. On the 20 tooth on this position A, it will only do a 1/2 millimetre and 1 millimetre. The 1/2 millimetre, any even number or just opposite numbers, this would have done 10 teeth of the 20 tooth pinion, so 2.5 inches, which is exactly 127 over 2, 63.5 millimetres. So a 1/2 millimetre one you can do at 2 positions. These other 2 positions here are somewhat unusual in that there's some gears inside here. Position B gives a gear reduction between the pinion and the dial of 5 to 1. And this enables 2 millimeters, 4, 1.25 and so on to be cut. Position C gives you a 6 to 1 ratio between the pinion and the dial. Now, this then means that 1 revolution of the dial in position B, if you're using a 20 tooth pinion, instead of being 5 inches, is now 25 inches. So instead of being 127 millimeters, it's now 508 millimeters. Now, that means that that's an integral number of pitches of all of these, and therefore you can engage at the correct locations as indicated on here. Effectively, what that's doing, that reduction, it's like saying instead of fitting a 20 tooth gear on the back here, we're going to fit a 100 tooth gear, which obviously would be much bigger, and it would just really wouldn't fit and not practical, which is why the gear reduction is done. And similarly 6 to 1. The downside on this is normally we run a 16 tooth pinion for an imperial threading lathe. That means that there are 16 positions around this dial for you to engage the thread, and obviously only a few of them work for the thread that you're trying to cut. Once you add the gear reduction in there, on this with this 20 tooth pinion, at 1 to 1 there will be 20 positions where the half nut in here will engage. Once you've added the 5 to 1 ratio, there are now 100 positions around here. So the gap between an engaged position and its next engaged position is now 3.6 degrees. It's not very much. Hence the need for this box here, where the magic mechanism in here only allows you to engage at exactly the right point. So you can use this without this, but it's very difficult. I've tried, and the likelihood of making a mistake is very high. Similarly, on the 6 to 1, it goes round extremely slowly, and re-engaging on exactly the right number is, you need very sharp reflexes. Right, so I've moved the trip block into approximately the right position, done it really tight, we don't want it slipping, and I'm going to run the lathe now full speed and thread with the tool well clear of the work and see where it cuts out. Right, now if I wind the tool in, I'm now going to advance the compound to put the tip of the tool right there. Right, so now let's come in. Touch off. here's the final thread. I've cheated and off camera. I've taken a couple of little spring passes just to bring it to size, but now we'll measure it on camera. There we are, 10.3. There's a lot of stick out from the chuck, and there is a bit of tool pressure making it very, very slightly bigger here. But this is just a demonstration, so I'm going to stop there. But there we are. That's a 1mm thread cut on an imperial lathe, disconnecting the half nuts. For this final demonstration, I'm going to cut an M8 by 1.25mm thread. So first, looking at the threading dial, 1.25 here needs position B, and you can engage on any number. Now this is useful, being able to engage on any number, because the dial is going to be revolving at a fifth of the speed it did previously. So the lever is on the side, and probably needs, like most gearboxes, to be whittled around until it's neatly engaged. Back to our threading chart on the lathe. So for 1.25mm, BS3W. So put the gearbox in neutral. Free wheel there, BSW, and three. Right, let's touch off and get this thread cut. So here's the thread, let's give it a measure. .31, bang on. So there we are, it seemed to work. Did I like it? No. If you look carefully, normally when you're using a dial with 16 teeth on the bottom, 8 divisions on the top, and a 4 TPI lead screw, this thing will engage bang on the numbers or with a fixed offset. With a 20 tooth gear on the back, a 5-to-1 reduction inside, engagement points don't seem to be bang on the numbers each time, and it differs from number to number. And I've got a feeling that I might well have hit one of the wrong points, just on the wrong side of the number. So yeah, needs a bit more practice, but it's definitely not the panacea that it might appear to be. Well, there we are. Bit of a long-winded demonstration, but finally got to the end of it. My thoughts on this: it's nice to have, but would I spend out on one, considering it's £500 sterling, 600 US dollars? No. But it came with the lathe, so I'm not going to throw it out. Well, that concludes the series on this. Thanks very much for watching.